Okay, welcome back. Let's continue. Today we'll introduce the other neighbor of a set, namely a group. In the previous two lectures, what we've seen is, if we go back to the diagram that I gave in lecture 11, that if we take a set of almost any object, and if we take a field of scalars, be those real or complex numbers or integers or anything else, then what we can do is we can define a linear combination, the plus operations and multiplication by a scalar that would give us a space. And if we further take a space and put a scalar product and a norm together with it, we get a Hilbert space. So in order to get a space, we needed addition and we needed multiplication by a generally complex scalar. What we will explore today is a slightly different object, which is derived from a set by defining a binary multiplication operation, where we take two elements and we give that pair of elements a unique correspondence to another element in the same set. And the resulting object, as we'll see in a moment, is called a group. Groups can be finite, groups can be infinite, but they are constructed by taking a set of objects, in most cases we will have them as operators, and defining a product which in most cases for us will be superposition. So this is just a repetition of the diagram which I gave in the 11th lecture, and it is reproduced in your handout for convenience. So to summarize this, the spaces in the case of operators are operators and their linear combinations. Hilbert spaces are operators, their linear combinations with a scalar product and a norm, so a notion of distance. And now we'll define a group which would be operators and superpositions of operators. So while we did not consider matrix-matrix products in this area, we will now consider matrix-matrix products on a set of matrices, and that will give us a group. Right, so we'll start with a formal definition of a group, its basic properties, and I will slowly move closer towards spin dynamics, because generally the theory of groups in its perhaps rigorous formulation is too general for our purposes, and so I will be jumping backwards and forwards between the mathematical definitions and the actual specific cases that we'll encounter in the context of magnetic resonance simulations. Right, so if we have a set G, and we have a binary product on that set, we'll call it a star, that takes a direct product of two copies of G into G, so it takes an element of G, another element of G, and maps it into the third element of G. It's called a semi-group, not yet a group, a semi-group, if it is closed under that product. That is, for any elements G and H belonging to G, the product G star H, or I will just briefly denote it GH, should belong to G. So if we have a set and a product on that set, and the set is closed under that product, then this is a semigroup. Right. If we demand two extra properties, namely that there be a unique unit element on this set, so if additionally there exists such a unique element, we call it a unit element, belonging to G, such that 1G equals G1 equals G for any element G belonging to the set. And also, for any element G belonging to G, there exists a unique inverse G minus 1, also belonging to G, such that G minus 1 is the same as G minus 1. G is equal to the unit element. Then G is a group. So the three criteria, which we will be testing again and again today, is there should be a binary product mapping two elements of G into another element of G, that there should be a unit element in G such that under that product, that unit element times anything else returns that same thing. And there should also be, for every element in G, the so-called inverse, such that when G is multiplied into its inverse, it should return a unit element. Now, in a special case, when the group is commutative, when GH equals HG for any G and H in the group is called abelian. These are particularly simple groups, as we'll see. But in general, the definition of a group does not require it to be commutative, so a class of commutative groups are called abelian groups. Now, obviously we can define a subgroup if this G has a smaller subset, which is also closed under the multiplication and has these same properties, then that is a subgroup. And the two groups, just like spaces were, will be called isomorphous if there is a one-to-one correspondence between those two groups. And the correspondence is linear with respect to all the group operations. Right, well, examples are quite plentiful. Because you're chemists, you had symmetry group theory in your quantum chemistry courses. You more or less know what a group is, so we are just repeating something that you already know. But an example from specifically spin dynamics is a group of propagators. So if we have H, that is a Hamiltonian, what it will have is its Hamiltonian superoperator. So H commuting with anything will be H double hat. And that will have an exponential, x minus I double hat t. The exponential propagator of the kinds that we have already seen several times. Now let's take a look at it. What can we do to two exponential propagators? Let this be t1, and let's take another element, x minus I h t2. Well, we can multiply them together. We can apply them sequentially, and the result will be the third propagator. The result will be, if we multiply the two, will be x minus I h double hat t1 plus t2. Another propagator, but for a longer period of time. And for a static Hamiltonian, it always commutes with itself. We can do it. So what we have here is the first property that is satisfied. The product of two elements belongs to the group. The product of two propagators is also a propagator. So at least the set of propagators is a semigroup. Well, what we can do next is test for the existence of a unit element, and it is quite obvious if we put the time to 0, the exponential of a 0 matrix is a unit matrix. Unit matrix does nothing, unit matrix times an exponential returns the same exponential, and so this property is also satisfied. The third property, the existence of the unique inverse, well, the inverse of this exponential is quite obviously plus I h t1, and if we multiply the two, we get a unit matrix, and it doesn't matter which order we multiply them in, and so we have all the conditions for a group satisfied. Furthermore, because for a given Hamiltonian we can apply them in any order, the Hamiltonian commutes with itself, we also have the propagator group as an abelian group. So you can see instantly the set of perhaps the most important objects in time domain spin dynamics, the exponential propagators, turn out to be a group. What I've assumed here, of course, implicitly is that these are unitary exponentials, that is, that h is Hermitian. In situations where we have relaxation superoperator in the system, so instead of H we have a Liouvillean, L double hat, that is H double hat plus I R. The nature of the relaxation superoperator can be such that it would send a few elements to 0. So it would not be a one-to-one correspondence, it will, for example, send L plus to 0, and it will send L minus to 0, irrespectively of which specific operator that is on which nucleus. So an action by R is in a sense destructive and irreversible. And you know from thermodynamics that such a process is irreversible. And so under such a Liouvillean, we might in fact be unable to locate the inverse, because it wouldn't be possible, at least for some relaxation superoperators, to actually invert its action, because it loses information as it goes. And so, in the presence of relaxation, the set of all propagators would be a semigroup. It would not be a group, because even though the unit element exists, the existence of the inverse is not guaranteed. And so, under just the Hamiltonian dynamics, we have a propagator group, and under dissipative dynamics, we have a propagator semigroup. As we'll see in a moment, these properties will come really, really handy. Other examples of groups, well, there are just point groups, symmetry groups, for example, a benzene molecule, the well-known D6H to all of you, you're chemists. If we flip the molecule, let's say, around, or we rotate it by 120 degrees, we get the same molecule, the particles are fundamentally identical, and so this also has a group of symmetry transformations, because two symmetry transformations in sequence are also a symmetry transformation. There exists a unit transformation when we do nothing, and there exists for each flip, flop, and rotation an inverse flip, flop, and an inverse rotation, and so the group of symmetries of a molecule, the point group, is also a group. And finally, and we'll see that in the next lecture when we symmetrize the spins, things like the metal group, H, 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 in liquid state, when the metal is rotating and the three protons are indistinguishable, actually obeys not just C3b, which would be the geometric point group of this, but in fact each proton can be swapped with every other proton in any order. The three are magnetically identical. And so the group that they obey is the full permutation group S3. And generally the permutation group of an object is called Sn, is also a group. And we'll give the rigorous definitions in a moment, but you can see that this group is quite special in that it has a continuous product. So in principle there are infinitely many propagators, and so A, this is an infinite group, and B, this is a continuous group. Whereas the group of symmetries of benzene is clearly a discrete group, there is a finite number of possible symmetries, and the group of permutations of the three protons just has 3 factorial, that is 6 elements. So clearly there are groups which are finite, and there are groups which are infinite, and we'll have to look at those kinds. Well, I've given the definitions, I've given a few examples, but here comes the point where these definitions become really too general to be useful. So what I will do from now on is to specifically assume that we are working over the fields of real or complex numbers. I will specifically assume that we are working with matrix representations of operators and not just any operators. This is reasonable because really we are only interested in things that practically occur in quantum mechanics, whereas mathematicians are in general interested in every possible realization of a group. But for our purposes it will be easier to understand and easier to apply if we from this point onwards actually switch to the specifics which are intrinsic to quantum mechanics. Right. What I will now do is introduce a notion of a finite and infinite continuous group in a little bit more detail. So if we have an element G in a given group, which would be, well, just a general case, either continuous or not, and we'll look at the elements of this G. So let's say that this square is the biggest group possible? Yeah, the biggest one. The first question we need to ask is what is the biggest group possible, and let's try and think about what is the biggest possible group made up of, let's say, n by n matrices. So if we have n by n matrices, and we want that to be a group, well, clearly if we take two matrices and multiply them, the result is a matrix. So the set is closed, so any matrices of a given dimension, any square matrices are a semigroup. Unit matrix is clearly there, so it's not a problem, but the problem is the existence of the inverse. That is, not all matrices are in fact invertible. So in order to make this into a group, we must impose a condition that the matrices be invertible. So the group of all invertible n by n matrices is known as general linear group, GL, of dimension n. It could be a group over complex numbers, it could be a group over real numbers, various particulars change, but this is a group of all invertible n by n matrices. So all the groups of specific matrices, for example, we can ask for a group of all Hermitian matrices, the inverse is also Hermitian, and the product is Hermitian, so it would be a group, but it will be subgroup of GLN. So in a sense, this is the biggest possible group of matrices n by n, and so we can erase this little biggest here and say that this is GFN. Well, so our group G has to be therefore a subgroup, or in fact itself, of GLN. And we would like to take a look at the neighborhoods of individual elements. So let's say the elements of our group are somehow scattered inside GLN. So this would be G1, this would be G2, and so on and so forth. So what I will now look at is the neighborhood of each element. And you see, the notion of a neighborhood requires there to be a metric. It does need there to be a norm, and this is the reason why I made the transition from a general mathematical context into quantum mechanics, because in quantum mechanics, in the previous lecture, we have just introduced the notion of matrix norm, and so this would not actually cause us any problem, whereas in the most general possible case, we would have to build the norm on this set as well as a scalar product. So, working in our matrix operator space, the one we are quite comfortable with by now, we actually know what the norm is, there's a trace definition. So, for a given element G belonging to G, that is a subgroup of GLN, and for any positive integer epsilon belonging to the field R, the set of all operators H such that the norm of G minus H is less than epsilon is called an epsilon neighborhood of the element. Epsilon neighborhood. And so if we just draw a tiny little radius around this element G and call that radius epsilon, so all the operators inside this little ball around G, a specific element, is called an epsilon neighborhood. Now, you see, if G is a discrete group, we'll only have a few such points. So conceivably, there may be a situation where, in fact, we draw the epsilon neighborhood and it exists in GLN, but it would not contain any other elements of G, like in this picture. So we've got element here, 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 but none of them are in fact inside the unit ball, or inside the epsilon ball. If this is the case for all elements of the group, so if for all such G's belonging to the group, there exists such an epsilon that all neighborhoods around them do not contain any other elements of the same group, then the group is called discrete. It may well be infinite, but it will be countable. So in the case where there is nothing in each neighborhood belonging the same group, the group is discrete. Now imagine a different situation. You remember our propagator group had a continuous parameter. So if we start with a propagator for time 0, so the unit operator, then the propagator for a little bit will be pretty close to the unit operator, so somewhere here, and then the propagators for further subsequent times will continuously depend on that parameter, and so what we'll have is that group, and actually it will eventually loop on itself. There will be such finite time as it will return it to the unit operator. This would be, in a way, a continuous line. And of course, in this case, if we take a specific element and draw an epsilon neighborhood around it, however we shrink that epsilon neighborhood, there will always be elements of the same group inside that epsilon ball. And if that is the case, the group is called a continuous group, and the other word for it is Lie group. And the Lie groups will be chiefly dealing with for pretty much the rest of the course, because they are the groups that describe the spin dynamics, the rotations, and quite a few other things. So that is the definition of a continuous group. So the groups can be finite, like the symmetry groups. They can be infinite countable, like the groups of crystallographic symmetries, for example, or they could be continuous groups, in which case they're called Lie groups. Right. Well, we can take another look at these continuous groups and try classifying them further, because really the groups that we'll be dealing with in the context of spin dynamics are considerably smaller than GLN. For example, the actual transformations that we have to look at must preserve the wave function norm, so they must be unitary. And a group of unitary matrix is a subgroup of GLN, but it's a smaller set. So let's now classify the various subgroups of GLN and take a look at them a little bit closer. But firstly, what I'll do is introduce something called parameterization for a group. So this continuous group has to be, well, continuous, and it has to be something called a differentiable manifold to be a Lie group, and a differential manifold has a parameterization. So what will follow is perhaps a rather obscure piece of mathematics, but it is necessary because we need to have a self-contained definition of these things. It will crop up again when we deal with the algebras in the next lecture. So a group is called a continuous group or a Lie group. That is, well, a continuous group when for each operator, so for each G belonging to G, there exists an epsilon neighborhood such that there exists an operator valued function, so G, of several parameters, T1 all the way to Tk. Remember, propagator group didn't just depend on time, it also depended on the strength of all the interactions that were there, so there are multiple parameters in general. That is continuous. Within that epsilon cube, so within modulus T I less than epsilon, that defines all operators in this epsilon neighborhood. And defines all operators. There. And furthermore, has different values of these parameters for different operators. So that is to say, if there is a unique, unambiguous parameterization of the group in each epsilon neighborhood by whatever system of continuous functions, then this is well and truly something called a Lie group. Furthermore, if there are k such parameters, the group is called k-parametric, or equivalently k-dimensional. That is, this number k of the parameters is known as the dimension of the group. Okay, well, let's enumerate a few groups that we will encounter in practice in our calculations. As I already mentioned, most of them are considerably smaller than GLN. We'll almost never be actually dealing with GLN except for various definitions of representations. Of course, all representations necessarily will have to be in GLN because that's the biggest matrix group there is. But very rarely actual physical dynamics. So, groups. Firstly, the biggest one, GLN. So all invertible n by n matrices. A slightly smaller one, and it arises in situations where we need to preserve volumes and orientations in our dynamics, clearly a fairly frequent requirement. SLN, special linear group. It is all invertible matrices of the same dimension with determinant equal to 1. And because determinant in a sense is giving us the extent to which the angles and volumes are preserved, that is necessary, and for the reason of there being this extra condition, this is called a special linear group rather than the general linear group. Well, we have to deal pretty often with unitary transformations. This is what quantum mechanics is about. Wave function norm has to be preserved, and the group of unitary transformations is known as UN. So all unitary n by n matrices. If we are working with a real space, not a complex one, unitary group would operate on the space of wave functions, which is complex. But if we're dealing, for example, with rotations, it is also a continuous group, parameterized, for example, by Euler angles, although it's not the best possible parameterization, but still, it will be something called orthogonal group, ON, so all real orthogonal n by n matrices. Right. Very often we are not just interested in any unitary groups, but we are interested in special unitary groups which preserve angles and volumes. So what we'll now do is combine the unitary group with the specialness criterion, and we'll get SUN, the famous SUN, special unitary group, all unitary matrices with determinant 1. And this is something that we'll see a lot in spin dynamics. If we look at the dynamics of a spin half, the dimension of the matrices is 2. All transformations, because they have to preserve the norm, have to be unitary, and they also have to preserve the angles and volumes, and so the determinant has to be equal to 1. And so the group of time dynamics, for example, on for a spin 1/2 is necessarily therefore SU2. If it's spin 1, in the most general case, it's SU3 because we have 3 quantum states, but very often it is in fact confined to SU2, which is a subgroup of SU3. And finally, because we often would like not just to have rotations and inversions, but just simply rotations without the inversions, we can have SON, which is a group of all orthogonal matrices with the determinant equal to 1. And the determinant equal to 1 ensures that there are no inversions in there, which would have determinant -1, for example. And so this is the group of rotations in n-dimensional space, and in particular what we'll be dealing with a lot is SO3, which is the Lie group of rotations of our ordinary dear old 3-dimensional Cartesian space. So all orthogonal matrices with determinant equal to 1. Okay, this is the grand scheme of things, and the two groups that we'll be mostly dealing with in this course are SUN for spin dynamics, SU2 mostly, and SO3 for rotations of the molecules, which actually reflects then upon the generators of SU2 and the spin dynamics. the grand scheme of things, I will now erase it and give you a bit more definitions as to the representations of the things. Now, clearly, these groups are populated by, well, in general, some operators, and we saw that some operators, particularly in angular momentum theory, can be pretty nasty. They're differential operators, not very convenient to work with. And because we're mostly working on digital computers and we would like to crunch matrices and vectors, a very important question is how to represent these groups with matrices. Therefore, how to construct the representations of operators that didn't necessarily have been matrices at birth into GLM, and to work with them there, because the computer will be able to multiply them very quickly and get us the answers that we would like to have. Right, so we will call P a map from our group G, which could in general be a group of any nature at all. Time translation, simply translation, rotation, whatever, into GLN. It is called an n-dimensional matrix representation if for any G and H belonging to G, the operations are conserved by the representation. That is, a representation of their product, GH, is the same as the representation of G multiplied by the representation of H. And similarly for the inverse and the unit, so the unit element of G has to map into the unit matrix in GLN, and the inverse of a given element has to map into the inverse of the corresponding matrix. And in that case, what we have is something called a matrix representation, and you can see why it's called a representation, because really all the operations that we had on the original group are mirrored into the group of matrices, and if necessary and if possible, there are difficulties, as we'll see in a moment, we can map it back. So that is a matrix representation of a group. Now, representations come in several flavors. You probably remember in quantum mechanics how we built matrix representations of operators. We were fixing a basis, we were calling it, for example, phi, and then phi I, an operator phi j, was a matrix element aij. So when you are computing such products, and you're all comfortable with these products, this is an integral and so on, to give you a matrix element aij, you maybe didn't quite realize that, but you were in fact computing something called a faithful representation of operator A in a given basis, which was necessarily a subgroup of GLM. So we'll now put a little bit more rigor on it and give the various flavors of the possible representations. Now, representations can be, firstly, faithful. A representation is called faithful when there is no loss of information under this map. So different elements of G are mapped into different matrices in GLN, and this map is reversible. We can construct a map back from GLN into G, and no information will be lost. In that case, the representation is called faithful, and you all know how to build one example faithful representation. So if we've got PG, so it is a matrix representation of an element G of a group. I'll put a hasn't just to remind us that this is in reality our practical reality and operator. That will be, so if we would like an element nk of that resulting matrix, for a given basis, it will be phi n, G, phi k. And so if we loop it over all the elements of the basis, we'll get the matrix of this G, and that would be a representation that would in fact conserve all the properties of G. We all know that a matrix formulation of quantum mechanics, Heisenberg's formulation of quantum mechanics, is equivalent to the wave function formulation of quantum mechanics, which is due to Schrödinger. And this is an example of a faithful representation in a given basis. Another example of a faithful representation wouldn't use a particular basis, but would use instead a group itself. You see, because this operator can multiply another operator, the group can in principle just modify itself. And so in a sense we can use the rest of the group elements as a basis. And so see how they transform amongst each other, and then use that to construct a representation. And that is known as a regular representation, which is also faithful. Regular. So, if we define numbers, delta, upper index I, j, k, such that gi, the element that acts, times g, j is equal to delta I, j, k, g, k. Remember, there are no linear combinations in a group, and so we can only map this product into a single element. We cannot get a linear combination, so this is always the case. Then these can be made into matrices. So if we do it like that, so P, G, element, and K will now be, so it will be G, I here, so representation of an element I, it will be delta, I, and K. And it's easy to see if you do a little bit of checking on these matrices that it is in fact a faithful representation which can be inverted back into the group. But generally the regular representation isn't particularly convenient because it tends to be bigger than other representations which are also faithful and generally is reducible. So whereas the dimension of this representation is equal to the dimension of the basis, the dimension of this representation will be equal to the number of the elements in the group. And if we've got an infinite group, such as a group of propagators, in principle, if we're only interested in a specific subspace of our quantum system, the faithful representation would be finite dimensional, because we only have, let's say, in the case of a spin, just 2 or 3 levels to work with. But the regular representation, because there are infinitely many propagators, might actually be infinite dimensional. So, in quantum mechanical context, although these are sometimes encountered, we often use the representation that's due to Heisenberg. Right, so they're both faithful, so they don't lose any information. Now let's give an example of a lossy representation. That is a representation that is actually losing information. For example, when 2 elements are mapped into the same element inside GLN. One example is the so-called scalar representation. When we take a group and map it into GLN faithfully, but what we then do is map it into R by just taking a determinant. It will in general just be the complex numbers. So clearly quite a few matrices in GLN will have the same determinant, so when we map it into C, the information will be lost because the reverse map is not available, but what we have is that this condition is in fact preserved. So if we take a product of the elements here, it's mapped into a product of matrices here, and the determinant of the product is a product of determinants, and so the relation in fact survives in here as well. So this is a valid representation, but it is a representation which is at this stage in fact losing a lot of information. This may be a bad thing, this may be a good thing if the information that we are losing isn't in fact useful in any way, or the system doesn't go there, then we may be satisfied with an unfaithful representation, and that's one example of those. And finally, the perhaps worst possible representation is the so-called trivial representation, where the entirety of G is just mapped into a unit matrix. And again, this holds, so it is a valid representation, but clearly in this representation we have lost all information about the group, because we've mapped it into a trivial subgroup of GLN, which only contains a unit matrix. Right. Another definition, you see we mostly do definitions here and perhaps connections to the practical realities of magnetic resonance calculations of equivalence of representations. So if we have P and Q, they are two representations of the group G of the same dimension, then P is equivalent to Q if for every G in the group there exists some similarity transformation such that QG is a similarity transformation away, so omega minus 1 PG omega from a P representation. So clearly this will have to be either unitary or orthogonal for that to work, and the representations would have to have the same dimension. And in that case, if for every element of the group this representation is just a similarity transformation away from that representation, then the two representations are called understandably equivalent. And interestingly, we wouldn't prove it, but I noted the fact in your handout that all representations of finite groups are in fact equivalent to unitary representations. So there will be such a transformation that will take any representation of a finite group into a unitary representation. It's fairly easy to prove because if it didn't, then the group would just explode. Okay. Now the next thing, and this is an analogy with the spaces, as you'll see a pretty close analogy, we will define a notion of direct sum and direct product of representations, and also the notion of reducibility. This is important in practice because we often seek, when we deal with our Hamiltonian, to either diagonalize the matrix, if we can, or block diagonalize it because it reduces the amount of calculations that we have to deal with. In other words, we seek to take a representation of our Hamiltonian and partition it into the smallest possible blocks in such a way that we can then go to a computer and process those blocks independently and therefore accelerate our calculations. Right, so if P and Q are representations of a group G on a space Cn and a space Ck respectively, then a direct product of these representations is a set of all such matrices of the form PG, Kronecker product QG. And we can easily check that this is in fact a representation by verifying the representation condition that this operation preserves the group properties. So if we take such a representation of GH, so it will be PGH cross QGH, so a direct product representation of GH. This will have to be equal, because individually these are representations, to PG, PH, cross QG, QH. Now, a cross of products is a product of crosses in matrix algebra. So what we'll have is the PG cross QG times PH cross QH, and that is exactly what we'd like to have. So GH maps into GH, and therefore this cross product of representations is in fact a representation. So that defines a product of representations. And just as we did for spaces, we can also define a sum of representations, and this will just be blocking together of the representations that we already have. So if P is a rep of G in a space Cn, and this space has a decomposition into a direct sum of other spaces, that is to say, this is equal to Cn1, direct plus C2, direct plus so on Cns. And this decomposition is such that these subspaces are invariant under the elements of the group. So the representation is blocked up. Then the representation P is a direct sum of the corresponding representations on these subspaces. So it will be Pn1 plus Pn2 plus so on P and S. In other words, what we simply have in this case, that if the matrix of a representation of G is block diagonal for all the elements, so not just for a single specific matrix in the group, but it has the same block diagonal form for all elements of the group, then this is called a direct sum representation. And individually, of course, these blocks are also representations, and because they are independent. The next important question is about reduction of representation to, in a sense, the minimal possible form. What we always have in magnetic resonance is Hamiltonians, which can either be diagonalized or block diagonalized. And in many cases, what this leads to is a considerable reduction in the amount of work that we have to do. Because what happens in practice, if that is Hamiltonian is block diagonal, we can print the blocks separately on a computer or even in parallel. They've got a smaller dimension, they require less memory, and therefore processing can be done considerably more efficiently. So the next question we'll consider is about the reduction of representation to ideally a diagonal, but in practice, because we'll have to do it for every operator simultaneously in a group, simultaneous diagonalization is rarely possible, but simultaneous block diagonalization is often possible, and this leads to what's called irreducible representations. They're the smallest possible blocks that we can break the representation down into. Right, so if we have a matrix representation P of group G, then the representation is said to be reducible if we can bring all matrices simultaneously into the following form. P1 of G, X of G, P2 of G, 0. That is, the representation is reducible if all matrices corresponding to all G's in this group can be simultaneously brought into the upper block triangular form. So P1, P2, and X are blocks of this matrix. The reason why this is called reduction is, in a way, this partially decouples at least parts of the system. You see, if we do a forward time propagation, then P2 affects P1 through X, but P1 does not affect P2, so P2 does in effect evolve its part of the system simultaneously, independently, although that part affects something else. Now, if X were to be a 0 block, this would of course be particularly simple, and if this is possible, the representation is called fully reducible. So if we can get it into this form, P1, G, P2, G, and so on, and we've got zeros on the off diagonal, so we just have individual blocks here, then the representation is said to be fully reducible. Again, I should emphasize that such a block structure should exist simultaneously for all G's belonging to the group, which makes it rather difficult because the number of such things in a group can in principle be quite large. If such representation is not simultaneously feasible for all elements in the group, the representation is called irreducible. And in particular, what we'll have is, once we've done the reduction, individual blocks would be irreducible representations of the group. Now, this brings us to a very fundamental theorem. It is called the Great Orthogonality theorem, which relates the elements of various irreducible representations of groups. It is a very important theorem. I will not prove it, we don't have enough time, but what we'll use it for is to derive the orthogonality of characters in the next lecture, when we start symmetrizing systems with equivalent spins. So, if we have two representations, one of them with a dimension NA and another with a dimension NB, of a group of order NG, then it happens to be the case that a sum over all the elements of that group If it is an infinite continuous group, it would have to be an integral over all the parameters of that group of the matrix element of a representation PA of an element G conjugate JK times a matrix element PB of an element G in representation PB, index LM, are orthogonal with respect to representations, orthogonal with respect to the first index JL, and orthogonal with respect to the second index KM. Now, this is not immediately clear what such a relationship means in practical calculations, so what I will try doing is draw you a schematic to show schematically how this works and why this is so important, in fact central to the theory of representations. Now let's take matrices of this representation for each G and stack them vertically like we would stack a deck of cards. So this is PA, and let's say this is the matrix of G1, and this will be the matrix of G2, and this will be the matrix of G3, G4, and so on. We just stack them vertically, and they have some elements. We'll take representation PB. It will have matrices of probably different dimension, but we can still stack them vertically like that. And so on. So this is PB, again G1, G2, G3, and so on. You see, matrices can have different dimension. Let's say this could be 2 by 2, and this could be 3 by 3 or something like that. But the stack will have an identical height because the number of elements in the group is the same for both representations. So what this theorem says is that, let's say, this column of elements and this column of elements are mutually orthogonal. So this is what is meant. We have an element jk of PA, so jk. We have an element lm of PB, so lm, and we are summing over the elements of the group, so vertically down the stack. And these columns, so any pair of columns here and here, because of this, are orthogonal if these are different irreducible representations. What this particularly leads to is the orthogonality of characters, but that is the focus of the next lecture. Right, the final topic for today relates to the propagator group that was mentioned at the beginning of the lecture, and in particular to the notion of a system trajectory. You all know what a system trajectory is. If we start from some initial density matrix and propagate the system forward in time, we get a collection of density matrices at each point in time. And that stack of density matrices is known as the system trajectory. Now, it happens to have a name in mathematics, and that stack of density matrices is known as the propagator group orbit. What we have to define in particular is something called the group action. I will remind you what a usual simulation consists of. It's x minus I h double hat t rho 0. So this operator is our G belonging to the propagator group, and this is just some vector belonging to our state space. Let's call it V. So the element of a group acts on this vector. Furthermore, we can say that we can act with an element with t equals 0, t equals delta t, t equals 2 delta t, where delta t is our time step. And so we are acting, as it were, with each element in turn, parameterized by the time t, and this parameter is inherited by the trajectory here. So we take each element of the group in turn, and we apply it to our initial vector. This is known as group action, and the rigorous definition is that if G is a group of operators, and A is a set, it could be a space if we have linear linear combinations defined in it, then the map G acting on A and taking it into A is called a group action by a group G on a set A. In non-abelian groups, we will have to separately define right and left action because they might not be the same, but that's a technicality. Now, in particular, what we need to know is whether there are some parts of A which remain the same under this action. So if there is a subset of A which is static under G, so it doesn't leak anything into the bigger set, then that subset is called stationary under the group action. So if we have a B which is a subset of A and G, B goes into B and does not go out into A which is potentially bigger than B, then it is called stationary or equivalently invariant under the action by G. Now, if every element of B additionally doesn't actually move under G, so in the case of invariance, we could in principle have A, then B, but there could be some movement inside B under this action. But if there is no movement at all, then the subset is called fixed under the action G. So if for any B belonging to B, G, B equals B, they're fixed. So frozen completely. This is important in the context of conservation laws, for example. If we have a conservation law in the system, then what will happen is it will partition our state space into subspaces with specific values of the conserved quantity, and those subspaces would be invariant under G, under the action by the propagator, but there could be some dynamics inside them, and in principle there could be subsets which are actually fixed under G, that is, they don't evolve at all. For example, there are those long-lived states. They are actually fixed under the relaxation superoperator. And there are many other situations in which this is important. This is necessary because it allows us to save time. In the simulations, we don't need to simulate fixed subspaces. We can just keep them frozen in time and later add back to the simulation, for example. Now, let's define an orbit. So we've defined an action, and so now we understand what this is. And the set of all such vectors into which the initial state is taken under the action of the group is known as the group orbit of that state. So strictly speaking, if we have a group and we have a set acting on it, then an orbit is defined like that. GA, so group times an element of our set. The orbit of A under G is defined as GA, where G belongs to G. So the entire set of such results. I will remind you that G is usually an operator in our case, and A is a state vector, or G is a superoperator, and A is the vectorization of the density matrix. Now clearly, in order to have this set in an orderly fashion, we'll have to enumerate these elements somehow. In this case, they are enumerated by a continuous index T, and therefore the set of all such products here for all the possible values of T ordered by T will of course be the system trajectory. So the system trajectory is the propagator group orbit of the initial state. The reason why orbits are important is they actually partition the state space. So if we have a state space V in which our system can potentially live, and we start from a particular point and there is an orbit that somehow loops the system around the space, and if we start from another point and it loops the system around the space somehow, then it is a proven fact. Again, I will not give you the proof, I'll just send you back to the literature on the theory of groups, that these orbits never have anything in common. So they are actually belonging to orthogonal spaces and they do not have any vectors in common. So the set of orbits, the set of group orbits from each individual starting point in the space is a partition of that space. So they are disjoint. Interestingly, the set of these orbits is actually a space in itself, and it is known as the orbit space of that particular group action, and this is denoted as V/G. But that's a technicality, I don't think we'll need it for any specific purpose. If it so happens that we have conservation laws in the system, and the action by G is leaving particular point in that space invariant, then a reasonable question we would like to ask is which specific elements in the group G are actually having these properties. There could be many of them. So the set of all G's, so all such G's belonging to G as leave a particular element invariant is firstly a group. So a subgroup of the group we're looking at, and secondly is called a stabilizer subgroup. Stabilizer subgroup GA. So given an element A, the subgroup of elements of G that leave it invariant is the stabilizer subgroup of our group G. Of course, there can be situations where the only element which leaves a particular vector invariant is a unit element, so-called trivial stabilizer, and if all stabilizers are trivial, then the group action is called free. This is quite infrequently the case because typically we do have conservation laws in spin systems, and therefore stabilizers are not all trivial because some states under some Hamiltonians are almost necessarily stationary. For example, the LZ state under the LZ Hamiltonian wouldn't move, and things like that. Okay, that's it for today, and we shall be dealing with finite groups and symmetries in spin systems.